All right, thank you very much, and thank you all for joining in. My name is Emily Gorcenski. I am a data scientist with ThoughtWorks Germany, though I am calling in digitally from the United States today. And so maybe you were around this morning when my colleague Arif and myself talked about continuous delivery for machine learning. That talk was about uh, how and why machine learning makes the practice of continuous delivery difficult. Um, in this talk, I'm going to go a little bit more into use cases and experience that we have seen at various clients throughout the world, really, um, about why it's hard to build data-driven systems. So while this talk is called CD for ML, I actually want to expand that thinking around machine learning and expand it to data-driven products in general. Um, so just by way of introduction, I do work for ThoughtWorks. We're a global consultancy. They've been generous enough to support us as we are exploring sort of these new frontiers of technology development and allowing us to go around the world speaking about it. And then, of course, due to the pandemic, we're all here gathered digitally. But we do work with businesses of all sizes. We have about 5,500 people around the world in 14 countries now. And we see all sorts of problems from all sorts of scales, from large multi-hundred thousand people organizations to smaller startups of 100 folks or so. And some of the patterns that I will be talking about today come from our learnings and our experiences with clients of various different sizes. You may have heard of us because we also published the ThoughtWorks Tech Radar. This is sort of a way to keep your finger on the pulse of what is happening in technology. And this initiative that we have called Continuous Delivery for Machine Learning has been in the last few editions of the Tech Radar because we believe in continuous delivery in general as a way to build software products. And when we start looking at incorporating data into that, there's lots of difficulties that come along with that. But we still do believe that if you're in the business of building data-driven products, that you should be looking to do so in a continuous delivery way, even though it is harder than building software in a continuous delivery manner. Um, so I keep talking about continuous delivery, and maybe you're familiar with it, or maybe you're at least partly familiar with it. But as we talked about this morning, and as we'll talk about here, what's important about continuous delivery is it's not a tool, it's not a framework, it's not a service, it's a culture. It's a way of thinking about software. And when Jez and Dave wrote the continuous delivery book 10 years ago, they had this wonderful quote there that it's about the ability to get changes of all types. That means features, bug fixes, configurations, whatever, into production, um, mainly into the hands of users, safely, quickly, and sustainably. And so that's sort of the North Star that we have here, is that we want to think about building data-driven systems in ways that can react to change, because data-driven systems can change many, many ways, many more ways than deterministic software can change. We want to do that in ways that is safe and reliable and sustainable. So continuous delivery is about continuous improvement and delivering quality products to the users in a way that gives you fast feedback. Why do we do this? It's actually, yes, we get quality benefits. We see improvements in the products that we are making. But ultimately, this is done because it makes our lives easier as developers. The faster we have feedback, the better we know, or the sooner we know if we're doing the right job. The faster we get feedback from users, from automated build systems, etc., the better we are able to understand if we are building the right thing and if we are building the thing right. So continuous delivery is a way of improving the developer experience, also a way of improving the customer experience. So the central thesis of this particular lens of continuous delivery and machine learning is this, what I will state without proof as a fact, is that machine learning models have a shelf life. And what that means is that we know that it takes some amount of energy and time to train a machine learning model. We have to collect the data. It takes sometimes years to collect enough data to build an effective model. We have to clean that data. We have to condition it. We have to do feature extraction. We have to understand its statistical properties. And all of that takes time. And then when we build it, um, we have a machine learning artifact at the end of that process. But data doesn't stay fixed. Data is constantly changing because the universe is constantly changing. Data is nothing more than a measurement of the universe at a point in time. It is an approximation of what we see in the world. It's an approximation of our ability to look at the world. Um, and models are an approximation of our ability to understand the world. So when we use data, when we use a series of measurements about the universe, we're trying to build an approximation of that universe. But when the universe changes, that model also has to change. And so sometimes your model might be valid for years. Sometimes it might be valid for weeks. I've seen situations where a model has run its course, it expired, so to speak, because the underlying conditions of the universe changed. And in that particular case, we were building a fraud detection algorithm. For whatever reason, whether it was that a new password breach happened or whatever, the fraud behavior changed. And that model was no longer relevant. And so what happens is that's a serious risk to a business if you don't have the ability to quickly retrain, quickly redeploy a machine learning model. We'll take a step back a little bit, but I want to talk about why data-driven systems are different than deterministic systems. So when I say deterministic systems, what I mean is your typical maybe microservice, or maybe it's your front end or your back end or your data pipeline. But what I refer to there is what we think of as typical software. And typical software should be reproducible. It should be testable. You should be able to audit it. You should be able to understand what's happening. And it should also be continuously improvable. We should know that we can build a website and maybe one feature isn't ready, but when it's ready, then we can put that feature into the website without having to rebuild the entire website from scratch. Right? Data-driven systems are not necessarily like this. They are non-deterministic by nature. They are built on the statistical properties of the data, which you cannot understand until you actually have the data. They usually have complex acceptance criteria because they're usually encoding complex business logic. They tend not to be auditable. They tend to be black boxes that are very difficult to understand. And they can be highly nonlinear, which means that they're difficult to improve. It's not a simple task to simply patch a machine learning model, because what you're effectively doing is trying to edit the optimization gradient of some cost function, and that's a very difficult thing to do. In other cases, what we see with deterministic systems comes from a product point of view. Requirements often flow down from the user. We have the sort of agile methodology where we write a user story. As a user, I want to click on the button to check out to buy my plane ticket. And we usually have a known and discoverable value of truth, right? So when I click on the plane ticket, when I click on the purchase item button, I expect that my plane tickets will be booked and that I will receive an email. We can write those criteria around that. And we can observe that behavior, right? So we can instrument when that button gets clicked, we can instrument when that email gets sent, and we can validate that these things are happening. But in a data-driven system, these are not always the truth, or not always the case. Here, often what we see are insights flowing upwards from the data. So we want to extract information from our data. We want our data to challenge our assumptions, which means that it's sort of like the old Henry Ford quote. If you ask people what they wanted, they wouldn't have told you a car, they would have told you a faster horse. So in this case, we need our data to inform us that cars are possible and faster horses are not. With data-driven systems, we may never discover what the known source of truth is, right? So no matter how good your analytics are, you probably can't decide why I decided to buy red Gatorade versus blue Gatorade at the grocery store, right? Because that truth is not a simple function of things that we can observe. It's a function of my internal emotional state as a purchaser. And you can intuit all sorts of things based on my past purchasing behavior, but you may never know what I was thinking at the moment of checkout. And finally, observing the system changes its behavior, which means that when we implement a machine learning product, when we start doing things live, creating feedback loops, we actually start to affect the behavior of our system. So if you're building a recommendation engine and you're telling me to buy this product because other people like me have bought this product, soon that's going to have an impact on downstream recommendations, on my purchasing habits, etc. There's sort of ripple effects that happen. And then finally, I often talk about how data cuts through abstraction layers. Deterministic systems, we can set nice abstraction boundaries, things like front ends and back ends, and um, model view controller paradigms, and we can even get real, advanced about it. We can write things in sort of functional programming languages. We can use these concepts to build code without side effects, quote unquote, modeling our systems using category theory. But in data-driven systems, that's not always true. Data tells you what it tells you and nothing more. That fact will cut across your abstraction boundaries. And you can't sort of invent data that wasn't there. And once you aggregate data, once you remove information, you can't get it back. My background is actually in mathematics, and in mathematics, we actually sort of refer to category theory as generalized abstract nonsense. Many mathematicians don't find it as useful as many computer science folks seem to find it. And so it's actually funny because when people ask me, oh, you're a data scientist, you must love functional programming. I'm like, well, I do love functional programming, but not because it's like math, because it's actually not. And then finally, when we have data, we have this property that a single example will disprove a hypothesis. So you may have a million records that shows that your users do blah, but if one person does something different, then your entire universe has changed. And so you can't assume things based on the majority behavior. That's not enough. So data-driven development is hard, and we're all kind of bad at it. But we can get better. That's the purpose of continuous improvement, is to take what we have, take the good bits, and improve the bad bits. But there's a reason that we're all kind of bad at it, and that's because it is difficult. And not everything that we have, the tools, the practices, have adapted to. So part of what we are trying to do, what I'm trying to do, is identify what are the tools, practices, and cultural challenges that make it difficult to deploy data-driven products in a continuous delivery sense. So a little bit of a background about me. As I mentioned before, I'm actually a mathematician by training, and I also studied aeronautical and mechanical engineering. And for the first 12 or so years of my career, I worked as a research engineer. So I sort of came into data science through the old-fashioned route, which is through computational mathematics, worked in neural networks before neural networks were cool, but after they were cool the first time. So in the in-between when they weren't cool and I was kind of a neural network hipster. And so in that process, I learned a lot about the process of developing complex technology. And so in the engineering world, when we're building things like rocket ships that send probes to Mars that like have this complex rocket that like drops a crane with the rover on it, all of these things, really cool stuff. But these complex technologies have to be managed in certain ways. And these things go from cutting edge basic technology research all the way up to system test launch operations. And so there's a scale that NASA developed in the 1970s called the technical readiness level. What this this is like a measurement of where various technologies were. And this is used to assess what are the right types of criteria that we should be using to assess a technology. Because it's a different set of criteria when you have a production system versus a type of system that you're building in the lab, right? You don't want to put all of the constraints that you have in your production system in your laboratory environment because you'll never get anything done. But you also can't take the flexibility that you have in the laboratory environment, put it into your production system because your rocket will blow up and people will die, and that's bad. We want to avoid that. So the scale is about thinking around your expectations and the different outcomes um, that you should expect for the level of investment. And this is relevant in the data science world because one of the things that we see is that data science is very research oriented. It's far more research oriented than software engineering. Most of the time, when we're doing new things in software engineering, it's because we're using a new framework or a new paradigm, but we're not reinventing the computer. We're not reinventing how to program. In data science, we're often taking brand new, or not necessarily new, but novel data sets, and we're looking at them in new ways and trying to build something new out of them. And the only way that we know if we can actually build something out of the data set that we have is often to build an effective thing out of the data set that we have. In other words, there's no way to estimate. The estimation is the doing. And so what we have is we see that data science work tends to skew towards very research-oriented workflows. And those workflows are not the same as production software engineering workflows. Um, and then, along these lines, I also kind of want to call out in this process that this is, well, it seems novel in the AI machine learning space. It's actually not, because we do this all the time in the BI world, but we just don't think of it in the same way, right? There's actually not that much difference between doing machine learning and crunching on your quarterly revenue forecasts that are using ARIMA models to forecast your growth or something like that. Actually, the mathematics of it is fundamentally the same. Um, and so we can't exclude how we treat BI systems from this discussion, if for no other reason that BI systems are responsible for most of the data engineering workloads in our organizations, and that affects how we do data science as well. Um, so that said, what is it that we need to do to get to a continuous delivery state? And in our talk this morning, if you haven't seen it, you can watch the video later. We kind of go through this. Building a continuous delivery um, capable machine learning infrastructure is quite complex. Obviously, you need to start with discoverable and accessible data. You also need your version control and artifact repositories. But unlike a software project where you can just simply use GitHub and everything that you need will fit there, that's not the case when you have petabytes worth of data that you need to somehow create a version system around and understand what is your test data, what is your training data, and have that be reproducible. You can't just take that and put it in Git. So you need better strategies around that. Same thing with your compiled artifacts, which can be a gigabyte or larger. You need to have a repository for those artifacts. You need a continuous delivery pipeline, so you need a build tool and a deployment tool that is able to orchestrate multiple pipelines. And by pipelines, what we mean are machine learning training pipelines. We also mean software build pipelines. We also mean data pipelines for shepherding data from one place to another. You need infrastructure for multiple environments where you can run multiple experiments live in your production systems. So in a software system, we might do A/B testing, we might do blue-green deploys. In machine learning, in order to scale to true continuous delivery, you need to go to a much more complex set of deployments to be able to support running multiple models in production at the same time. So rainbow deploys or other types of deployments that allow you to collect more data simultaneously. Along those lines, you need to be able to track the performance of your model, both during training time and in production, which couples with observability, where you need to have your systems instrumented properly so that they're creating a feedback loop so you understand what is happening before problems arise. So with all of that, with this sort of complex set of things that you need to do, we see lots of people trying to implement this or shortcut this in various ways. And so there's 6 patterns that I want to talk about where I see organizations sort of stumbling on this. So these are 6 things that hurt. The first, and it pains me to say this, is that there are too many data scientists. Um, you probably don't need as many as you think. You just need to make sure that if you're hiring them, you're giving them the right amount of work. Um, one of the challenges here is that data science is a fairly new field, and there are still only a few number of ways to get into the data science field. We see the same sort of archetypes of data scientists over and over and over. Um, one of those archetypes is sort of an academic who has maybe left year 5 of a postdoc to come into industry. And they're very smart. They're great with data. They're great with coming up with solutions and doing research, and they're diligent and incredible additions to your team. What they usually lack is software delivery experience. And you need to really ask yourself if you need actually PhDs who are neural networking experts when your system probably only needs a logistic regression model built. Um, if you do need PhDs in your teams, then you need to surround them with an equally deep supporting cast. It doesn't do you any good to have a PhD that's running off in his own little corner and not giving them the expertise in infrastructure and software engineering and all of those things to actually bring their products to life. So one of the common anti-patterns here that I see is a team of lots of data scientists. So 4 to 8 in a team. What they do is they build a model, right? But they don't have any connection to the business case. And so it takes them 12 to 24 months maybe to get this model into a production ready state. Because they're running experiments, they're doing, sort of randomized controlled trials of the model. And because of this slow sort of return on investment, this slow delivery cycle, there's often pressure for the teams to do more work. And so what we see is these teams of like 4 to 8 data scientists undertaking, 3 to 5 or more work streams in parallel, but none of them are going to production. And so they're not actually getting any feedback in a meaningful way in what they're building. There's another thing that we have to talk about when we talk about academics. Because they don't have a lot of software delivery experience, their code quality often struggles. This is academic code that was written by somebody who's very smart, but this is not code that I would accept in a production environment. I would not even accept this code in a system that was just being used to train a model. Why? Because it's not being tested, because it's, hundreds of lines of a single function. We're doing inline functions in this code where there's very little context here. So what we want to do is we need to train our data scientists on how to work with code as if it is software. One of the patterns of this is that data scientists are often working in notebooks like Jupyter or Zeppelin notebooks. My colleague David Tan, who is with ThoughtWorks in, I believe, Singapore, has written a wonderful article on the coding habits of data scientists, on how to transition from that early phase discovery work that is suitable for notebooks and understanding when it is time to stop using the notebook and start turning your software, your code into software. And so he talks about refactoring notebooks to turn them into testable modules, and specifically what it is around the notebook workflow that is incompatible with continuous delivery as a concept. So there's a link here that you can check out later, but I highly recommend reading that article. This is not to call out academics to say that they're bad software engineers. This is simply to say that we have to get over this hurdle in order to get us to a continuous delivery state. Second anti-pattern that I see is overcomplicated solutioning. Everyone thinks that their competitors are building a super AI that is like super smart. They have better data. They're going to like outmaneuver us because their AI is so much better. Probably none of your competitors have a super AI. Probably all of your competitors are right around where you are, which is trying to implement basic machine learning into their production systems and succeeding to varying degrees. And so what happens is rather than taking an incremental continuous improvement approach, trying to build the smart AI because you've seen other people build the smart AI and talk about it at conferences. Um, this is not the right approach, right? So if you can't ship a logistic regression to get you your 70% of your optimal gains, then you probably can't ship a convolutional neural network to do the same. And all of the TensorFlow serving and all of the, MLflow um, stuff is not going to get you there, um, because it's not about building, it's not about having the right tools to build your complex model into your software. It's about having a culture that allows you to do continuous improvement. So if you have nothing, or if you have a hard-coded rules engine or built around business logic, then your first step should be seeing which of those things you can turn into a basic model and see what types of gains you can get there. Because most of the time, most organizations will get their biggest return on investment from implementing a very simple, tried and trusted regression model. You don't need to go to the complex things. Furthermore, along these lines, there's a pattern that exists where people look for problems because good solutions exist. Like we know that the convolutional neural network is really good at image classification, which is great unless you don't have an image classification problem, and don't try to turn a problem that you have into an image classification problem simply because convolutional neural networks exist. The third anti-pattern is that the wrong tools are being used. We, as data scientists, love experimentation and prototyping, and our workflows are built up around that. So notebooks are designed for getting things out the door fast. This makes production fast, or development fast, experimentation fast, but production is hard. Moreover, we're seeing a sort of explosion of tools in the data space, lots of tools handling things like versioning and serving and blah, blah, blah. These tools are trying to do, in my opinion, a bit too much. We need to cut the boundaries a little bit better. I don't necessarily want my versioning tool to also try to spin up, my Kubernetes cluster to host the model. I want my data versioning tool to be really good at data versioning, and I want my deployment tool to be really good at deployment. And I don't want this. There's no single step solution from from end to end. What I want is those tools to do their jobs better and to integrate better with each other. We've seen this in the DevOps space where we had tools. We went from a world where we were just kind of writing bash scripts all the time to understanding that actually we need better tooling. And now we have a fairly mature set of um, frameworks and tools and packages and things that help us do things like manage our cloud deployments, that do things like help us stand up observability, et cetera. Like Grafana is a great dashboarding tool to help you instrument your systems. It's not trying to be the thing that deploys your Kubernetes cluster, and it shouldn't be. We don't kind of, in data science, the tools are kind of getting a little bit built too large. Similarly, we're seeing the wrong metrics being evaluated for our, both for our models and for our teams. What we're seeing is that we're optimizing around academic or abstract fitness or objective functions. These don't necessarily link to business value. It's great if you can get improved accuracy. If you can improve the accuracy of your image classifier by 10%, that's wonderful. Great job. How does that correlate to actual revenue? If it doesn't, you're probably wasting time solving an academic problem that doesn't actually bring you any money. Moreover, when we start looking at production machine learning systems, we haven't yet adapted our reliability culture to build these systems with the right service level agreements and service level objectives. So things like latency, uptime, those are all nice things to have if you're building a large distributed web system. They don't mean as much if what you're doing is around data. And so we need to have a culture of building reliability engineering around things like data accuracy, data freshness, um, having certain statistical properties, having certain performance characteristics versus how fast, what is the latency, how available is your system. Uh, Another anti-pattern also in the BI world is that there's too many dashboards. We're seeing lots of organizations building many, many, many dashboards, um, which a dashboard almost instantly becomes technical debt the minute that you build it. Oftentimes, the code necessary to put together the data is often SQL code. It's not living in a source control repository. It may not even be being written by somebody who has formal training in data engineering. So what's happening is you're building all these dashboards to hunt insights, um, and then those dashboards are decaying. That's costing you money because you have to maintain those systems. It's costing you transparency in how your organization is operating because you can't review that code, you can't test that code, and there's no way of knowing if that answer that it's giving you is the right answer. Moreover, um, data should give you a path to action. The worst thing that you can do in data is to give somebody a wrong piece of information. But the second worst thing that you could do is to give somebody a right piece of information that is very interesting and potentially very valuable, but not let them do anything with it. Like, don't give me a taste. Either give me nothing or give me something that I can use. So if you're building, if you've got more than one dashboard per person in your organization, you probably can't empower every person to act on everything that dashboard is saying. And then finally, we talked about insights earlier, but I also think it's an anti-pattern to be mining for insights. I've seen lots of organizations where they put data scientists in the team, and because the data scientists aren't able to integrate well with the production software, they're not able to create OKRs or team metrics that allow them to be connected to this actual product that's being developed. And so what they do is they end up creating OKRs like, we're going to, in quarter 3, we're going to come up with 5 insights. Well, that doesn't do anything because those insights are as soon as you find them, they're already old because the data that created them is already old. So if you can't act on that insight immediately, and if you're not empowering your teams to take actions based on findings, including taking actions on findings that run counter to your expectations and counter to your ongoing initiatives, your insight mining is actually going to be a cost sink and not a revenue driver. So all of that said, that concludes the portion of Emily Yells About Data, because there's actually patterns that do work that have been developed around sort of these, watching these anti-patterns grow and evolve and ultimately fail inside of organizations. And so some things that work, actually, I'm going to borrow a metaphor here from my background as an engineer in control systems engineering. So I talked earlier about closing the loop, using the data that you get from your systems to close the loop to create feedback. You can sort of describe any feedback system in terms of a controller, a plant, or a model, which is how the universe works, and sensors, which tells you how you're doing. And so this is your feedback loop, right? And if you think about this, you can break this down. And so what you can control is embedded in your controller. What you can't control is this bit up at the top coming into your plant. Those are your externalities. The plant tells you how your system will behave, whether that system is your website, your business, whatever. And then what comes out of the plant is the truth, right? The universe is a perfect simulation of itself. So whatever is happening is the truth. But you can't see the truth. You can only approximate it. And that's what data is. Data is your approximation of that. So we want good sensors to give us a better view of what the reality of the universe is, what is truth, and we want to be able to use that data to take actions that change the universe to what we want it to be. And so what you can do is you can build better user experiences, you can build better models, You can build models that incorporate data faster. You can also measure more things. You can build better sensors, right? You can measure things more accurately. You can measure things more often. And you can make measuring things easier. That's data engineering in a nutshell. And so if we want to think about what we can observe and what we can control, um, these are the sort of the thinking that we want to create in order to build an effective continuous delivery team. And by the way, machine learning has two domains. It can either live in the controller, where you're trying to use an AI to make automated decision making, or it can live in the plant, which is using machine learning to model your systems to understand how they behave so that you can try other things. So both of those things are necessary. Oftentimes we're too limited in our thinking about AI as being purely a controller or purely a plant. And by the way, BI systems, which consume still the most amount of our data, are often living in the plant. They are systems that are trying to understand how the plant has operated and how the plant will operate in the future. That's why BI and machine learning are very close cousins. They're not two separate things. We shouldn't treat them as two separate things. But if we want to be a data-driven system, we have to incorporate all of this into a feedback cycle, which means accounting for every part in a continuous delivery way. So I said before that continuous delivery is a cultural transformation, not a technological one. This is the most important bit, right? Because what this means is that it's not about building a tool, it's about building a team, right? The unit of software delivery is the team. And so we need to ask ourselves, we want to build a data-driven product. Do we have the right team? Um, are they given the right authority? And do they have the right resources? Um, so in some organizations, yes, you can put together a team of data scientists who, keep their heads down, and every once in a while they chuck a model over the wall. That works if your organization is large enough and you can afford to also staff a team of data science engineers or machine learning engineers to productionize that work. Not every organization can afford that. Also, it's very hard to find machine learning engineers. The data engineering market in general is very much skewed towards the data engineer and away from the employer right now. But we've also seen that just putting a data scientist into a cross-functional team is rough because data scientists often don't have the experience with software engineering workflows to integrate as closely. So what that means is that we need to understand that a data product needs to have a delivery plan. So you can't just throw a data scientist into a team to make your product smart, nor can you just take a bunch of data scientists and put them in a team and expect smartness to diffuse through your organization somehow. You actually need to have a delivery plan from the beginning, from the inception of the product. How are we going to productionize it? What is our use case? How does our use case affect our data? What do we need to make that happen? Moreover, a few years ago, all the talk was about build a data lake to enable your data scientists. That's great. You made it so that we don't have to write SQL, but it hasn't actually changed anything, right? The data is now just in an unstructured format in a bucket versus in a structured format in a warehouse, but it's still dirty. We still need to clean it. It still takes the most amount of our time. Along those lines, real pipelines have real messy data, which means that this is a constant battle because our systems are designed around operations. They're not designed around generating clean data. So this means that our models will always have messy data that needs to be cleaned in order to be trained, which means that this process being a lengthy and time-consuming process, we want to be able to do it as many times and as quickly as possible, which means that we need to be able to think about many things at once. We need to parallelize our development of models. So that means that we need to have the ability to run shadow models in production simultaneously and test them against our real production data. This will allow us to spin up lots of different parameterizations, lots of different modeling approaches to understand which ones perform better against the actual real data that we see. But there's a caveat with this, that if you can only have one model in production, if you're running your multi-arm bandit system or whatever, you might have one for the stable, one for the test. Um, but ultimately, we have to understand that the open loop performance and closed loop performance are not the same thing. So while it's still valid and valuable to test shadow models, it's not the same thing. You will not see the same behaviors once you implement one of those models and promote it to production, because you'll start seeing changes in your customer behavior as soon as you turn it on. This was a great tweet from a couple of days ago. Um, this just sort of encapsulates the frustration that data engineers have. Lots of requests like this. Hey, can you just pull this data for me? Sure, let me just select star from some ideal clean and pristine table that you think exists. Um, it doesn't exist like that. That's not how it works. Um, the world isn't like that. Data engineering will always be time consuming and will always require the data engineer to understand um, the legacy, the history of the data, um, the needs of the use case, the needs of the consumer. And without those things, you won't actually be successful. So data engineering is as much technology development as it is archaeology. Finally, one of the things that we see is that succeeds is when we bring our consumer and our producer closer together in a domain-driven model. So in ThoughtWorks, we have a concept here called data mesh, which is around domain-driven data product development. And what this is doing is it's saying, put the people who need the data closer to the people who generate the data. When the DevOps revolution came, it wasn't about tools, it was about putting operational concerns closer to the developers, right? So literally tearing down the wall between the ops team and the dev team. We need to do the same thing with data. We need to make sure that we are putting the people who use the data, they should know who's generating it, because the more people you have in between, the more abstraction boundaries you have in between, the more difficult it is to understand the legacies of those data. And the more time it's going to take you to actually turn that data into value. So data mesh can be hard to accomplish because it requires you to put lots of different skill sets in a team, and the teams will tend to be a bit larger than normal. And so one possible alternative to this is to have a sort of a 3-team maximum, which might be one team that is responsible for the production of the data, your product team that is using the data to produce it, and it may be necessary to put an enabling team in there in between that has the expertise to the data engineering knowledge to get you the data that you need in a scalable way. But what we don't want to see is 7 platform teams in between consumer and producer. The reason that we want to do this is because every team that is in between your data that's coming in, those are your sensors, and the control that you can take. Every team in between is going to introduce a delay. And the more delays that you have in your system, the less likely you are to maximize the value of the data that you're seeing. And so what we want to do is we want to shrink those delays. We want to speed up the feedback loops. And that's what continuous delivery is all about. So that's all that I have. Ran a little bit short, but that's all right. I am happy to take any questions that you might have, talk about some of the case studies in more practical terms, or also just hear what you might have to say about challenges that you've had in building data products. So, thank you.